Right, today I'm going to talk about work I've done in collaboration with my colleagues John Good, Eva Dielman, Ryan Tanaka, and Karen Vahi. So why are we giving this focus demo? Well, we want to show how astronomers can take advantage of only open source tools to build workflows that they can build, test, and execute on-premises machines and clusters, and then, as far as is possible, scale them without modification onto distributed parallel platforms such as clouds or HPC platforms. So what we're going to show is proof of concept, and we're here to get feedback on its value and how we can develop the project further in the future. The demo is freely available on a shared risk basis, and a little later on I will give you the link where you can go and access it. So the two tools we have chosen for this focus demo are the Pegasus Workflow Manager and the Montage Image Mosaic Engine. Now, both these tools are open source. They operate by design on multiple platforms. They both support Python APIs. They are, at least we think, reasonably easy to use, and they do play well with one another. So a schedule of events. To start off with, I will give a very short introduction to Pegasus and Montage. I'll spend most of the time on Pegasus since people at ADAS are probably less familiar with it than Montage, which I've spoken about probably too often at previous meetings. Then I'll give you the link to the demo if you want to sing along with it. And then we'll go to the main event, which is a guided walkthrough of the Jupyter Notebook by my colleague John Good. It'll show you how you can make images like this one on the right of M17, which is a 3-color mosaic made of 2 mass data. And finally, I'll describe what happens when we tried running this on the Open Science grid, and then I'll give you a summary of the demo. So to start, let me talk a little bit about the Pegasus Workflow Management System. It's a fully featured workflow management system. It allows scientists to develop portable science workflows using Python, Java, or R APIs. In this case, we'll be using the Python API. And these workflows are structured as directed acyclical graphs. Scientists can then use Pegasus to run their experiments on heterogeneous resources, including your local machine or local cluster, clouds, HPC systems, and computing grids. Now, Pegasus also provides monitoring and debugging capabilities via command line tools, or if you wish, a web dashboard. If one of your workflow jobs does fail, you can easily debug the problem with tools such as Pegasus Analyzer. Another great feature of Pegasus is that it automatically handles data movement between jobs. Whether you are pulling input data from an S3 bucket on the Amazon cloud or need one job's output to be sent to another job, Pegasus will handle this for you. And finally, Pegasus runs your workflows with data integrity and fault tolerance in mind. You can have Pegasus perform integrity checks on all files used in your workflow, and if jobs or file transfers fail, they can be automatically rerun. Alright, so when working with Pegasus, you'll typically have an experiment or a set of computations that need to be performed, and at a high level it will generally look like the drawing on the left. So you can then describe your abstract workflow programmatically using one of the APIs, in this case Python, as shown in the center image. And once that's done, your workflow will be serialized to a YAML representation, which will be consumed by Pegasus and compiled into an executable one meant specifically for your own execution environment. So once your workflow is compiled, it's ready to run. So at the bottom row on this chart shows some of the most common execution environments where users can run their workflows. It includes cloud resources such as AWS or the Google Cloud, HPC resources such as Xseed or local clusters, and even resources such as the Open Science Grid. Right, so now I'll talk a little bit about Montage. It is an open source toolkit for assembling fixed images into custom mosaics. It's written in C because that provides performance and portability. We have deployed Python binary extensions of these C routines so that you can get compiled performance in a Python environment. Now the workflow in Montage is by design highly granular. There are separate modules written for each step in the mosaicing process, all the way from reprojection on the left and the chart on the bottom to co-addition at the right. And in the middle you have the background rectification steps. Background rectification simply means that you're rectifying the background of each of the images to a common level. In addition, this processing paradigm is embarrassingly parallel. You can process each of the images that you input into your workflow on independent machines, and you can use as many of these as you wish. So it's this granular workflow and this parallel processing that allows Montage to work very well with workflow managers. And in fact, we have used Montage with Pegasus before. For example, we built a 15 wavelength atlas of the plane of our galaxy in the infrared using purely resources on the Amazon cloud. So if you want to try out the demo, you can go to the link in the top right hand corner of this chart. We created a Docker image with everything you need to run the Montage workflow Jupyter notebook. The Docker image contains an installation of Pegasus and HT Condor. Pegasus sits on top of HT Condor, which actually does the running of the jobs for you, the Montage binaries, and the workflow notebook. Now, shown on the right, you can interact with this container through Jupyter Notebooks via the browser. You can even use this container environment to test out different workflow configurations if you wish to do that. Finally, the container contains Pegasus tutorial notebooks if you want to learn more about how to develop your own Pegasus workflows for different applications. And now let's begin the demo. I will hand over to my colleague John Good.
With Montage, you can build arbitrarily large mosaics. And since large portions of the processing can be done in parallel, you have the potential to do in days or even hours what might otherwise take 6 months. Using cloud or cluster resources, it is now feasible to marshal tens or even hundreds of compute instances and tens of terabytes of storage for short enough periods of time that the overall cost can be kept reasonably low. But effectively using these resources can be a major task in itself, and building an infrastructure that can effectively switch between platforms even more so. That's where Pegasus and HT Condor come in. As we shall show here, it is straightforward to explain to Pegasus how to use your tools to do the processing you want done. Then Pegasus will work out an optimal processing plan in the form that can be handed off to HT Condor, and HT Condor already knows how to run such plans efficiently on all these resources and more. All we need for plan building are the Python libraries for Pegasus and Montage. Montage is used here just to gather metadata about the actual data needed for the mosaic. When HT Condor runs, it will use a separate copy of Montage on the compute resource in the form of a set of Linux executables. The free parameters for the mosaic are the location on the sky, size in degrees, and the dataset. For Pegasus to do its work, we need to populate 3 data structures. The first, the replica catalog, is information on the files that will be needed as input, where they are, and how to retrieve them. It is called a replica catalog because some datasets can have multiple available copies of the files, and Pegasus can improve throughput by alternately using different copies. The replica catalog doesn't need to track all the files that are created during the processing. Pegasus will handle those. The second structure is the transformations catalog. Transformations are all the tools that create new data from old, in other words, the Montage processing modules. Again, Pegasus is capable of keeping track of multiple copies of these tools, though in a case like this, they will just be executables in our local path. Finally, we have the workflow catalog, which keeps track of all the processing steps we define, the transformations used, and the specific files needed as input and created as output. All three of these catalogs are maintained as SQLite databases. We can populate the transformations catalog up front simply by adding the paths to all the Montage modules we will use. The general flow for building a mosaic with Montage always uses the same set of steps, with variations depending on whether we need to reproject the images, which we almost always do, or correct the background levels. Even for properly flux-calibrated images, backgrounds can vary, especially in the infrared. The background there depends so much on where you are in the zodiacal dust cloud and what direction you are looking. The data taken over an extended period of time, here years, will have widely varying backgrounds. So, as we will describe below, we need to reproject all the images to a common frame, examine all the image-to-image overlaps to gather information on background differences, model a set of updates to the backgrounds that can minimize the residual differences, apply these updates, and co-add for a final mosaic. Our first steps are to define the WCS header for the mosaic we want to build and to search a remote metadata service to get a list of images we will need. Note we are not gathering the data now. The actual data downloads will be the first set of tasks in the workflow. It will be done when the workflow runs on the cloud. Various lists of files, the original data, projected images, difference images, background corrected images, will all be needed during the processing, and we can actually predict what these will be now. And so we can finally start building the workflow catalog. All the images listed in the original raw data table need to be added to the replica catalog. We don't need to explicitly call out a file download job for each one, as Pegasus will know how to get them and includes that step itself. We do have to define reprojection jobs for each image. We already calculated all of the image-to-image overlaps above, so now we can define the jobs that do that processing. In the workflow, these are set up so that they can be processed as soon as the reprojected images for each pair become available. So in the extreme case, where all the reprojections are done in parallel, as soon as the first potential difference pair complete, the difference job will start. While the reprojection and overlap difference fitting jobs can be massively parallel, the next steps for globally modeling the corrections focus down to a single thread. First, we combine all of the individual difference fits into a single table, and then we run the modeling code. This program iteratively estimates corrections for all the images and is optimized to be able to do this even with huge numbers of images in minutes. And while this processing does need to wait until all the reprojections and difference fittings are complete, those steps are fairly uniform in processing time, so will all tend to finish at about the same time. So in practice, this single thread step does not represent a bottleneck. Once we have the corrections, we can again spread the processing out and apply a background corrections in parallel. The final mosaicing step is, in this case, another focus point. However, for really large mosaics, we often find that in practice we prefer to co-add as a regular set of tiles rather than as a single image. Finally, we add in a couple of optional steps to create a fixed size PNG rendering of the mosaic. Remember that all of this was us explaining to Pegasus what we wanted done. At this point, we want Pegasus to work out an optimal processing plan based on our input. This diagram is a standard optional output from Pegasus showing the plan it came up with. Here, for a much smaller sky region, our graph gets ungainly with over an order of magnitude more difference nodes. The primary Pegasus processing in what follows is the line that reads workflow.plan submit=true.wait, which means we want Pegasus to make the processing plan and submit it to the local HD Condor for processing. We also want it to wait for HD Condor to finish. For a serious run on the cloud, we would decouple all this, building the plan and then later submitting it to HD Condor on the cloud to run in background. Here Pegasus will monitor the HD Condor run and report progress in real time. We won't wait for that to finish. We could expand on this workflow to process all 3 bands needed to make a color composite at the end, or more likely would submit the processing as 3 workflows. We've done that here and made this composite. It's important to note that no knowledge of Pegasus needed to be added to the montage code for all this to work, and that is generally true for Pegasus processing. It is true that for typical montage processing, one would capture and analyze the response messages from the montage modules to control the flow. This allows you to react to the processing and add conditionals and loops. Pegasus is more basic than this. It only checks the program return statuses and for the existence of expected output files. And this is a mode that works fine for well-defined pipelines of the sort described here. So if you have a set of processing modules capable of being used in a pipeline mode where parallelization is feasible, Pegasus is a natural.
Well, having run the workflow on our local machines, we then went and ran it on the Open Science grid. Now what we really wanted to do was run it on the Amazon cloud, but unfortunately we didn't have credits left, so we were not able to do that. The OSG is a good choice as a parallel platform because Pegasus works out of the box on the OSG Connect access point. We know this already, which makes it an ideal target for large workflows such as those provided by Montage. The Open Science Grid itself, or OSG as it's now known, is an NSF-funded project that facilitates access to high throughput computing. It is in fact free to use for any US-based researcher, and indeed in the past year it's provided over 1 billion CPU hours to researchers. Right, so what we did was we took our Montage workflow and ran it on OSG. It can be done with very minimal modifications to the Python workflow script. We did make several changes to take advantage of some OSG specific features. Well, first of all, we configured all the data movements to be handled by OSG's stash cache data infrastructure. Behind the scenes, the files are cached in an opportunistic manner that requires no extra effort on our part. Second, because compute resources are of various operating systems, and considering that we compiled Montage on Red Hat 7, in this case we wanted Montage to run on Red Hat 7 machines. We can achieve this by using RHEL 7 singularity containers that are cached within OSG's CERN VM file system. So setting this up required us only to change a few lines in the workflow generation script. Now, on the right-hand side, we show some metrics that Pegasus reported about our run on OSG. First of all, the workflow consisted of 332 jobs altogether. Now this number's greater than the amount of jobs we actually created in the workflow script because Pegasus adds in jobs to handle tasks such as data staging and cleanup. Next there is the workflow wall time, which, believe it or not, is the workflow wall time. And after that, the next two metrics show cumulative job wall times. So as you can see, there's some queuing overhead associated with running things on OSG. For very large workflow runs, Pegasus does provide a feature called clustering, where you can cluster groups of tasks into a single job to avoid such overhead for such small independent jobs, which are precisely the kind of jobs that you have in a montage workflow. In fact, the next step in this project is to actually use clustering to improve the performance of the workflow. Finally, well, we're happy to report that we have successfully run Pegasus on Montage on 2 platforms. Clustering of jobs on parallel platforms will certainly improve performance, and this is easy to do with Pegasus. Also, as our next step, we want to migrate this to the cloud. Pegasus will be especially useful in optimizing performance and costs. In fact, the Rubin Observatory has already used Pegasus in this fashion on the Google Cloud to study performance and cost optimizations. And finally, we invite everyone's comments and suggestions, and it remains for me to thank you all for attending and listening. Thank you.